Now, this morning, what we're going to have is the 6 steps, okay? 6 steps in performing a statistical hypothesis testing. Now, you have to understand that these 6 steps is applicable in most, if not all, statistical tests and how to do hypothesis testing. At least this is the manual procedure when we do the hypothesis testing manually. But with the advent of technology, we can actually skip all this part. But now, since we are just beginner, I would like to start at least you letting you embrace the basic of doing hypothesis testing manually. Since we don't have the software, available software in conducting test hypothesis for this one. Okay, now we will talk about the 6 steps of hypothesis testing. What are these 6 steps of hypothesis testing? Now, like I said, hypothesis testing it would actually, actually these steps are applicable in all statistical hypothesis testing. Okay, they varies only in some portion of the steps wherein there is a specific way what you're going to do compared to the other, but exactly all the six steps are present. Now, the first step is actually we are going to set up the hypothesis. Of course, first and foremost, it's hypothesis testing. So therefore, it is really important that you have to establish your hypothesis because it is what you're testing. Okay? So first step really is you have to be certain, you have to be clear about your hypothesis. Now, if I'm gonna walk you through this particular example, this is an illustration wherein there is like a physiologist, okay, by the person of Dr. Tony. This is just a imaginary character. This is not a true data. But for the purpose of discussion, I'm going to pick this as our example. So when you say statement of the null hypothesis or set up the null hypothesis, not set up, but rather state the null hypothesis, sorry. Although it means the same thing, but yeah. State the null hypothesis. So in this example that I am carrying, so I'm going to show all the 6 steps using this example by Dr. Tony. Dr. Tony is a fictional character. He is a physiology who made or who came up, who has this hypothesis that LLD women or having LLD reduces growth rate of women as compared to the women in the general population. So take note, this is an extension of our lesson last time with one sample tests. One sample test, it's simply there is this population and then you draw a sample, a random sample group from the population, and then you compare the mean of this population to the mean of the mean of the sample compared to the mean of the population. And then we're going to find out whether there is a significant difference between the two means now. Now, in this case, Dr. Tonin made an assumption or a hypothesis saying that having LLD reduces the growth rate of women compared to women as compared to the women in the general population. Okay, so a patient diagnosed with LLD would reduce the growth rate of women in coming from the population of concern. Take note, if you may ask what is LLD, it is accordingly leg length discrepancy. Okay, that's the meaning of LLD. So diagnosed with this kind of condition, according to Dr. Tony, affects the growth rate of women compared to the general population. The general population refers to the women in general. And then whoever or you happen to be diagnosed with an LLD, it means to say that it affects your growth rate. Okay? But in this instance here, that is Dr. Tony's, what do you call this? That is Dr. Tony's hypothesis. That's what at least claimed by Dr. Tony based on his observation and probably uh, just mere hypothesis of Dr. Tony. Now, take note, Dr. Tony in this situation, in his hypothesis, did not say that the height of the average height of the woman with LLD is they're taller than the average height of the general population of women. He doesn't say that. I mean, she doesn't say that. As much as she doesn't also specify that the height of this, the average height of this LLD woman is also um, way shorter than the average height of the general population. There's nothing statement like that. But in the event that Dr. Tonin would like to be very specific, like for example, Dr. Tonin would say the average height of this LLD patient or woman diagnosed with LLD is less than the average height of the general population, that could be more specific. Or taller than the general population, that is more specific. Now, why did I brought this concept? It's basically, it would somehow align to the idea when do we use two-tailed and one-tailed test, okay? If Dr. Tonin would say that the average height of the group, sample group, is greater than the average height of the population, then we are going to use one-tailed test because it's directional, meaning to say the population, the sample group mean is greater than the population mean. Or the other way around, that the mean of the sample group is less than the mean of the mean of the population. So that is directional. So one tail. But in this general statement of Dr. Tony that we have right now, she just simply said that the woman with LLD reduces their growth rate compared to the general population. So with that saying, there's a specific whether taller or shorter. This sample group, the LLD, the group of LLD women. So with that, it is a non-directional hypothesis. Thus, it's a two-tailed test. Take note, Dr. Tonin's hypothesis is the alternative hypothesis. It's the claimed. Now, always remember, there are the way to prove Dr. Tonin's hypothesis is actually there are several ways. The practical, I mean, without doing a statistical testing, Dr. Tonin can actually go out to the country, get or record the height of all the LLD women, and then get their average compared to the mean of the population, and then conclude. Okay, but do you know that the constraint of that act is very obvious. It's not possible. Definitely, it's not possible that Dr. Toyn can go around the country and look for all these LLD women and then get get the average of their height and then make a conclusion. That's not really possible. So the only way is that Dr. Tony can make a random selection of the LLD woman and then get their average height and then compare to the population height. Okay, so I have already walked you through that Dr. Tony's hypothesis here, research hypothesis is can be proven indirectly. Proven indirectly, meaning to say she doesn't need to go out of the country and then get all this LLD woman's height and then get their average. No, what she's going to do now is that she will prove it indirectly by simply coming up with the so-called hypothesis, another hypothesis known as the null hypothesis, which she intends to make it false, so that his or her claim, her result claim, which is now the alternative hypothesis, is true. So she will prove it indirectly by simply coming up with a null hypothesis and trying to prove it wrong, so that her claim, the alternative hypothesis, will become true. Now, take note, how do we write the null hypothesis for Dr. Thorne's case? We have H sub O. By the way, this is our notation. H sub O stands for, we read this one as H sub O, or H subscript O, That's the that's the long say of saying it, but the shorter way is H sub O, meaning to say null hypothesis. Okay, null null hypothesis. Now, how do we write the null hypothesis? Actually, to write the statement, the null hypothesis, as we state the null hypothesis, we need to know the population mean. Now, this is for the purpose of example. Like I said last time, there are informations or variables wherein there is already a renowned uh, mean of the population, which you can use at the same time the standard deviation. But in this case, we do not know one of the variables wherein getting the mean of the population is quite tedious is the height, because you need to get a sufficient sample to represent the height of the population. At least you need to have a good amount of sample to estimate the height of the population. Okay? So, but for the purpose of discussion, this time we'll just make an assumption that let's say that the mean of the population here is 65 inches. And then, by the way, in the real sense, we cannot make this assumption. This must be stated facts. Okay, like I said last time for the what do you call this one? The IQ and the SAT, they have the mean and standard deviation for the population, which are given already or at least standard. But this time, we'll just make an assumption. And then with the standard deviation, population standard deviation of 3 inches. Okay? Now, let us set up our null hypothesis. Setting up the null hypothesis is actually simply saying that mu is equal to mu sub O. This simply refers that the population, the mean of the population, and then the mean of the sample group. Okay, the mean of the population of the sample is the same. So meaning to say, the average height of the LLD woman and then the general population is just the same. Meaning to say, there's nothing that is observable in terms of fluctuation of height. So whether I'm an LLD, whether the person is LLD woman, and then or not, their average height are just the same. Okay, so there's nothing to do. So that's the null hypothesis. This is what Dr. Tonins she needs to make this false such that her claim is true. But take note, we need to quantify this. Okay? Because this is our purpose, our point of comparison. We need to quantify what is the population mean. Okay? That is represented by mu sub 0. Mu sub 0 is simply represented as x sub, mu equals 65. This is mu sub 0. So we will state now our null hypothesis to be h sub O is equal to the population of the sample mean and the average, the mean of the sample group is equal to 65. Meaning to say, the mean of the sample group is just 65 inches. There is no, or it's just exactly the same with the mean of the population. The average height of the population or the average, the normal or the woman in general population. So we stated already our null hypothesis, and I'm going to put it here. It says that the mean of the the average height equal. Okay, there's several ways how you can state that one, but basically it simply refers that the average height of the woman in the general population and then the woman with LLD, the average height of the woman in the LLD population is just the same or equal. So as we assume now that the average height of the woman in the general population is 65 inches, it means also that the average height of the LLD woman is also 65 inches. But we wanted to make this false so that Dr. Tony's hypothesis is true. Okay? So we will set up now. You notice in this instance, we focus so much on the null hypothesis. But we cannot forget that the original hypothesis here of Dr. Tony is that the height of the LLD woman, the average height of the LLD woman is different compared to the average height of the woman in the general population. So how do we state that? Using our notation H sub A, okay, this is the alternative. Take note, alternative, this is the hypothesis of Dr. Tony, which would say now that instead of the same, the population mean and the sample mean are the same, we will say that they are not the same, not equal to 65. So it varies. It doesn't specifically say whether greater than 65 or less than 65. That's why remember that whenever we have our alternative hypothesis in this situation, it's non-directional. So it could have been greater than or less than. So we have two rejection region that's both above the mean and below the mean. Okay? But in the event that Dr. Tony is certain that the average height of the sample group, which is the LLD woman, is greater than the average height of the population of the population of the general woman in the general population, we can state the null hypothesis as H sub A, the alternative rather as mu greater than 65, meaning to say they are taller. The average height of the LLD woman is taller than they're way taller than the general population. Or you can have it as A mu less than 65, meaning to say the height of the elderly woman, they are way shorter than the average, the woman in the average population, general population rather. So with that saying, this is now the directional, meaning to say there is only a specific direction where we reject the null hypothesis. But like agreed last time, the safest way is do not specify which direction because it could have been possible that we anticipated that the population sample mean is, I mean, the group sample mean is greater, and it turns out that the result is less than. So, like mentioned last time, we can no longer further continue. So, what can we do with this one? We have set up already our alternative and null hypothesis. So, the alternative hypothesis is basically the claim of Dr. Tonin that the average height of the woman in the general population is not equal to the average height of the woman diagnosed with LLB. Okay? As literally there, it's not equal to 65. So this is what we're going to prove. So you notice we have state now our null hypothesis, which is the first step of uh, the 6 steps in hypothesis testing. Actually, from the book, there was an assumption. It was just an assumption coming from this book that, uh, assuming that the height of the general population is 65 inches. So that was just an assumption. Probably there could have been a basis for this one, but a disclaimer was not stated that it is an actual fact. So this is just like a dummy information. It's not a real one.
Okay, sir.
But
Thank you.
basically, when you have a problem like this must be given, or at least we are dealing with variable wherein we know that there is a standard sample size, population mean, and standard deviation.
Okay,
Okay,
sir.
like for example, the SAT and then the IQ. I think the IQ is 100 is the standard deviation, and then the mean is, I'm not sure really, but I think there was, as I read some article. Our step two is we have to select the statistical test. Select the statistical test. And the significance level, or that is alpha. Okay? This is the step two. We are going to identify what is our test, our statistical test to be used. And then at the same time, we will now assign our alpha. That's why alpha is already or must be assigned before doing the hypothesis testing. That is the protocol. So you have assigned. Now, in our sense, in this particular part of our discussion, as this is about comparing the mean of the sample group to the population, we're using z-tests. Z-test. As we are using our t-table, our z-table, and then at the same time, we will assign our alpha to be 0.05 or 5% level of significance. Take note why I'm using this one, because in the field of psychology, this is the conventional alpha. Okay, this is the accepted alpha in the field of psychology. So we have 0.05 or 5% level of significance. And then the z-test here, because our discussion is about z-test. But later on, once we have already the t-test, the f-test, so you have to specify clearly as to what value you are going to use. And there is also, I forgot what table is used when we use the chi-square or for test of independence. Okay, so we have this second step. We have the select the statistical test and at the same time the significance level. So the third step is select the sample and collect the data. We will select the sample and then we collect the data. So in this case, if Dr. Tonin wants to know the LLD woman is shorter than the average, there is a definitive way to answer that. Accordingly, the definitive way to answer this one without doing a statistical test is, like I said earlier, Dr. Torin can go around the country and then look for this LLD woman and then get their height, then solve their average height. But of course, that is really the constraint of that is very obvious that it's impossible to do. So what can Dr. Tonin do is select a sample, and by means of selecting the sample is that is already step three. Select the sample and then collect the data that is intended. So in this case, let's make an assumption that Dr. Tonin randomly selected 16 LLD just for the purpose of example. Okay, we're done with step three. I'm just going to write here our sample. Let's say the sample is, where is the sample? Right, there is more additional insights. From the standpoint of hypothesis testing, the larger sample, the better. Of course, we all know that for a fact that the larger the sample size is, the better, because it is more likely will resemble the population's situation. As the bigger the sample size is it is approaching to a more, um, I mean, more sample would always go near and near to what is the actual population. That's why larger sample size is better. Okay? But, I mean, in the event of doing a larger sample size, that is minimizing the risk of committing type 2 error. But the risk of committing type 1 error basically relies on your alpha value. Because if your alpha value is 10%, then there is a greater risk of committing type 1 error. But if your alpha value is zero point 0.1 or that is 0.01, that is 10%, so there is a minimal risk of committing type 1 error. But according to this explanation here of this author, the more sample you will have, then that means to say you have greater chances of, I mean, there is a smaller risk of committing type 2 error. Okay? So let's record now our sample. According to this group, our sample size is 16. And then the recorded height of the 16 LLD women are the following. So these are the height in inches of the 16 randomly selected LLD women. Take note, randomly selected. Okay, because that is one of the assumptions that one should meet in conducting or performing a one sample test. Okay, so we selected the sample, we selected 16 samples, and then we collect the data, and these are the collected data for example purposes. Okay, but in an actual sense, you really have to go out there and then you have to identify your sample size, and then you go and get the height of these 16 samples if you have sample size of 16. Okay, but for the purpose of discussion, this is what we call a pre-existing data because or data because this was just like this was not gathered actual. So this was just a data that was just stored and then used. Okay, we have step one, two, and three. Now we're done with this steps. We are going to move now to step four. Take note of our values. Okay, the values that we have for our data here. So next step, step four. Okay, step four is find the region of rejection. Find. Okay, we are now going to illustrate where in our data we will reject the null hypothesis. Okay, now we understand that it's a two-tailed test because if you go back to our null hypothesis, it's non-directional. As stated that the alternative hypothesis is simply mu is not equal to 65. So it's non-directional because it does not specifically identify whether the mean of the sample group is greater than or less than the population mean. But it was just plainly stated that it's not equal to the population mean. The mean of the sample group is not equal to the population mean. So it's non-directional. It's obvious that it's a two-tailed test. Therefore, we are anticipating now two rejection region. And we have set our alpha to be 5% level. Our level of significance is 5%. So what we're going to do now, illustrating here our diagram. Okay. There are two rejection regions. Since our alpha is 0.05 divided into 2, our answer is 0.025. So this rejection region here, the probability of rejecting the hypothesis on the right side of our mean is simply 0.025%, while rejecting it below the mean is also the same, which is 0.025. So you notice our alpha was now subdivided into, was divided into two equal parts, giving us 2.5% both directions. So first here, if our probability, our p-value landed in this region and on the side, the right side of our mean, we reject the null. At the same time, if it landed here, left of our that is within the 2.5 beyond our critical value, then this is also reject null. By the way, we call this area here, the boundary, okay, as our critical Z. Okay, we call this area as critical Z. Critical Z score. So meaning to say, we have to identify our critical Z score. If I will ask you, what is the critical Z score of this value, knowing that this is our uh, the area of rejecting the null hypothesis. What must be the Z score here? You must know that one. That is our quiz last meeting. And in fact, our discussion as well. What you're going to do is you're going to subtract this from zero point 0.5. Whatever is left, that is the probability of this remaining area. And then look for this one in the Z table to get the Z value here. Like what we did last time. This is 0.025. So that's zero point 0.5 minus 0.025, you have 0.475. Then we look for this one in their table under probability distribution and then get the corresponding z-score for this to get the critical z-score. So you have 0. This area, the probability of this area here is 0.475. Now on the table, look for this, the z-score equivalent to 0.475. That is your z value. What's the value? Okay, it's 1.96. This is 1.96, the z-score here. And this one side here is z equals negative 1.96. It's the same, but the other one is in the positive while the other one is in the negative. But basically, the meaning of the positive and the negative z-score here implying that the rejection region here, the critical region here is above the mean, and then the other one is below the mean. Okay, so we have already specified our rejection region. So in the event that our p-value landed in this side here, or landed in this side here, that means to say, we reject the null hypothesis. Otherwise, if we cannot do so, then we fail to reject the null hypothesis as our decision. Okay? Next, we have found already our critical Z. Now, in the event, what will be the critical Z if our tailed test is one tail? What is our critical Z? Considering that still our alpha is 5%. Go ahead. So illustration-wise, it would have been like this. If it is greater than the mean, it's like here. What's the Z value here? And then this is 0.05 because it's just one tail. So what must be the critical Z? The Z value is 1.65. It's either positive or 1.64. It's either positive or negative. If it's less than, so that means it's a negative 1.64. If it's greater than, then that is 1.64 positive. Okay? So that is in the event of, just very quick, what about if our alpha, for example, is 0.01? In two-tailed test, what is our critical Z? Our alpha is 1%, and then we are using two-tailed test, still an indirectional hypothesis. What is the critical value, or what is the critical Z score? Positive and negative, still positive and negative. 0.015. Now that's the rejection area. If this is the case, so I think what you're referring to is this is 0.015. Well, this is 0.015. But I'm asking for the critical value here, the Z score. The Z score.
2.33.
What?
2.33.
It's not 2.33. That's basically 0.5 minus 0.015. It's 48, 0.485. Look for what is the Z score equivalent to 0.485. What is the Z score equivalent to the probability distribution of 48.5, 50%, or 0.485? Huh?
2.6. Six.
2.3.
2.66.
It's two. According from this book's example, it's 2.58. I'm not sure if it's 2.58 in your end. You look for 2.58 if it's closer to 0.485. Because I was not handling my own Z table. Anyway, if it is like this, more or less it's 2.58 or negative 2.58. That is if our alpha is 1%. Now we have already stated and um, specified our area of rejection. Once this is done, okay, we've done this part already. It says that if the z-score you calculated for experimental group is larger than the critical value, without having a look in the table, your p value will be smaller than the alpha. So there are several ways in how we're going to make decisions here. Later on, okay, we already associated our alpha, our critical z. Now, if our computed z, okay, later on when we do the computation, which is the next step, if our computed z is greater than this one, it means to say our p-value falls on the rejection region. That means to say we reject the null hypothesis. But if our critical z, if your calculated z, the computed z is greater than 1.96, that means to say we reject the null. But if our calculated z is less than this one, the critical z, then we fail to reject the null hypothesis. That is when we're going to base our decision in terms of our z value. But if our basis for z, our basis of decision is the p value, if the p value falls in this region here, or in this region, meaning to say it's less than 0.025 or less than 0.025 in this direction, that means to say we reject the null hypothesis. Okay? I think those were the two ways we can, or then the other way also is comparing our p value to the alpha. But since our alpha here was subdivided into two, our alpha is 0.05, right? That's our designated alpha. Now, if we're going to make our decision based on the alpha value, we're going to double our p value later on. Our computed p will be doubled, and then we compare it to alpha. If the doubled um, if the double p value is less than 0.05, that means to say reject the null. But if the double p value later on is greater than 0.05, that means to say we fail to reject the null hypothesis. So there are three ways on how we're going to uh, make our decision. If we can do it in terms of the z-score, we can decide it based on the value here of our p-value without looking for the z-score and at the same time doubling our p-value. And the last way is that we double our p-value and then compare to our designated alpha. We doubled it, it's because our original alpha here was actually divided into two. So that's why our p-value computed, the result of our p-value must be doubled so that as we compare it to the alpha, because the original alpha is actually still 5%. What I'm saying here is that there are three ways in determining whether we accept or we reject the null hypothesis. The first way is we compare the computed z, later we'll do the computation, compared to the critical z, which is this one. That's why it's nice also to identify the z-score. That's the first way of determining it. The second way of determining it is just we look at the p-value. Is the p-value landing on this region? From the critical, this bar here going there, or from this one going here? Or actually, we can just look at it on this one direction because they're just the same. That's 0.025. If our P landed to or happens to be greater than 0.025, then reject the null. But the third way of determining is simply we compare the p-value to the alpha. Now, if we compare the p-value to the alpha right away, then we double our p-value because the alpha original, the alpha was 5%. And the p-value was computed based on the split alpha into two. So we double the p-value, which is whatever is the result, and then compare it to the alpha. If the result is the p-value is less than alpha, then reject. If the p-value is greater than alpha, then fail to reject the null hypothesis. Okay? So that is exactly those were just my points why I said that there are three ways on how we determine our decision. The first way to determine the decision is by means of the critical value. Later on, step 5, there is what we call computed z. We will compute the z value based on the formula we have last meeting. And then that's the computed z. If the computed z compared with the critical z as this one, if the computed z is greater than this one, that means to say we reject the null. But if the computed z is less than the critical, this one, it falls somewhere here, then that means to say we fail to reject the null hypothesis. Okay? And then the second way of determining is we simply will compare our p-value. If our p-value is less than this one, okay, the transmuted or the alpha that was subdivided into two, then reject the null. But if the p-value is less than this one, greater than this one, then we fail to reject the null hypothesis. Those were the three, at least the first and the two. No, they're not the same because if it's one tilde test, what you're going to subtract from 0.05 is this one to get the probability in this area. This one. But if it's one tilde, we will subtract this one, this portion, which is 0.5, subtracted by 0.05. But the basis is always minus, it is subtracted from 0.05. It's because we're referring to half of the distribution, which is what is determined on our table, the table that we're using. I think that's your question. Whether is it always subtracted from 0.5? Yes, because our point of reference there is half of the distribution. We already specify our area of projection. Now let us move to the next step. We're almost towards the last step, which is we're now moving to step 5. Step 5 is, of course, what is step 5? That is calculate or compute the test statistics. We will compute our test statistics. But just to recall, our formula for z-score, the computed z-score is simply mean of the sample group, which is the LLD woman, minus the mean of the population, which we assigned earlier. Where was that? I think I erased it already, which is 65 inches. And then with our standard error, remember standard error? Which is given to us as standard error equals standard deviation, population standard deviation divided by the sample size, the square root of the sample size. Remember that? Okay, that's our given formula. Now, let us let's have our decision, or at least our computation. Let's compute our z. First, let's get our standard error. Our standard error, remember, I forget. We have to compute first our sample mean. What is the sample mean? If you copy the one that I have written here, can you please get the mean of that group? What you're going to do, 16, add all the 16 scores divided by 16 to get the mean. Go ahead. I'll give you a little time to compute that with what I have written down here, and then you give me the mean. Go ahead. I know already the mean because I solved it already earlier during my previous class. So, just stop me once somebody have already the mean of that data set that Did you get the scores that I have written here last earlier? Oh, what's the mean now? Mean of the sample, the mean of the mean height of the LLD woman.
I-divide siya into 16, sir?
Yeah, divided by 16 because that is
63?
just
63,
what?
sir.
63.
Okay, you got
63.
it 63. So if you
63.
notice the mean of our sample group, the LLD woman is actually 63. If we may recall, our population mean is 65. So you notice this is 3, that is 1, less than the mean of the average. Actually, I did not know also in this example, but there was just another assumption. We have an assumption that our standard error last time was 3 inches, right? Our not standard error, but standard deviation of the population. Because these are all needed. Now, if that's the case, our standard error is simply, and then our population, our sample size is 16. So you have 3 divided by the square root of 16, which is 3 over 4. This is our standard error. Now we need to solve for our z. Z value is simply our mean of the sample group is 63 minus the mean of the population is 65 inches divided by our what do you call this one? Our standard error, which is 3 over 4. So we have z, that's negative 2 over 3 over 4. So you have negative 2 times 4 over 3 equals negative 8 over 3. That's negative 8 divided by 3. You notice the rejection, our computed z is negative. So it falls on the left side. Okay. It is approximately 2.67. Z-score is negative 2.67. That is our z-score. Now, our z-score is 2.67. If you compared our critical z, crazy, critical crit z, forgot how to write that symbol. It's like this. Z cri is equal to positive negative 1.96, while the computed z comp is negative 2.67. Now let's compare which is greater, critical, the z critical or the z computed. Comparing this one,
Z computed.
Critical.
Critical.
which is
Z
greater,
critical.
z
Critical.
critical. So
Yes.
if that's the case, what's the decision? Meaning to say, this value here, this computed, falls on this area because it's moving here. Remember, the z computed is less than the z critical. Okay? Since the z critical is less than the z computed, that means to say, it falls on the rejection area. So, if I'm going to write it, that z critical is greater than z compt. So this is the situation based on the computation in step 5. So our step 6, okay, for our step 6, I'm just gonna write it here. Step 6, by the way, is we will make the decision now, or make the statistical decision. Make the statistical. Okay, we will make the statistical decision. Now, like I told you, there are 3 means to decide. This is the first one. Since the z critical is, this is sorry, this is wrong. Z critical is greater than the z computed because This is negative 1.96. And remember, for the negative numbers, the bigger the numbers, that is smaller, the number becomes smaller and smaller. Since negative 2.67 is bigger than negative 1.96, therefore, negative 2.67 is smaller than negative 1.96. That makes it Z critical is greater than the Z computed. If that's the case, the Z critical is greater than the Z computed, then we reject. Our decision is reject H sub O. We will reject the null hypothesis. Okay? We reject the null hypothesis. Based on this first, let's just look at this one. We now can say that Dr. Tonin's hypothesis is significant. That the height of the LLD woman is not the same. The average height of the LLD woman is not the same with the average height of the general population of women. That is in terms of critical Z. First, the other way of determining it is in terms of our p-value. Okay? How do we get our p-value for this one? Okay, since our p-value is this one, I don't know, this is our critical Z, let's get our p-value. Our p-value is computed like, you have negative 2.67. What is the probability distribution of 2.67? Look at your table. What is the probability distribution of 2.67?
0.4972.
49.72. That's subtract that one from 0.5. Wait. 0.5 minus 0.4972. Was it 7942?
4962, sir.
4962, sorry. So that is 0.0038. That is our p-value. Okay? That's the p-value for compare this so our p-value now is 0.0038. Okay, that is our p-value. Now, since that is our p-value,
Reject, sir.
what happened to this one here? Compare this one to the alpha. So since Z is, okay, aside from this one, another way of doing this is comparing our p-value with the alpha. This was already doubled because we computed it in terms of one direction. Okay? Okay, it is just a one direction. So you have now 0.0038 and then you have 0.05, which is greater between the two values. 0.05 or 0.0038. Since alpha is greater than our p-value, thus the decision is still this one. Yeah, my bad, sorry. This is not 0. Compared to 0.05. It should be 0.25. Okay? Which is still this one. The one that I told you that if you wanted, since we're doing a two-tailed test, if you wanted to compare it to the original alpha, you double this one, which is 0.076. Am I correct? 0.76 or 0.076? You try to double. 0.0038 times 2, 0.0076 compared to 0.025. If you're going to specifically, you look at, because this is our rejection region. If we don't like to use the critical Z and computed Z, and then we do not like to use the p-value compared to the designated alpha, sorry, this is 0.5. Okay, so if you look at this one, if you double this, if you double the p-value, this is our p-value. If you double this one, then compare it to the original alpha. Because we tried to fuse already the two sides of the rejection region. But if you wanted to focus with the p-value right away, write this one without doubling it, we just compare it to our designated rejection region here with a divided alpha. So if you look at this one, 0.38% is actually beyond 0. It is beyond the critical value, which is 1.96. So it falls on this region. This value is smaller than 0.025 because this value is only 0.38%, while this one is 0. It's 2.5%. So basically, this percentage here is greater than this percentage. Therefore, our decision is to reject the alpha. Reject the null hypothesis. But if you wanted to go this direction, this is the first attempt of making the decision. The second attempt at this one, the p-value compared to our area of rejection as specified in step 4. Or if you wanted to use the alpha right away, you have to double your computed p and then compare it to the alpha. Okay? So these are the three instances. But you notice between the three instances, we all have the same decision, which is reject the null hypothesis. So that's the end of the 6 steps. We ended up with the decision that we will reject the null hypothesis. Making now here the point that Dr. Tonin's hypothesis is significant. That the height of the average height of the sample group, which is the LLD woman, is not equal to the average height of the population or the general, the woman in the general population. Okay? So that ends the entire 6 steps with the conclusion or with the decision that we reject the null hypothesis. And then for the interpreting result for one. There is another here making in a decision, how do we interpret this one, 38, 0.0038. So it means to say 0.38%. Okay, by the way, the purpose of this one in an actual research paper, if we will use the APA format, that's American Psychological Association, when you report the result of Dr. Ton, for example, you conducted the hypothesis testing, and then you will report now the meaning to say you're going to write it in your research paper that the result is significant. Okay, I'll just make a quick recap of the 6 steps before we will take note of some of the restrictions and some of the things to remember in performing a one sample t-test using a Z test analysis. Okay, the first step is state the null hypothesis. Okay, first we set up a specific null hypothesis that we wish to disprove. That is what you need to do. Take note, your alternative hypothesis is your claim or the claim there is available. Okay, that is the alternative. And then you wish to disprove that one, or you wish to prove that one by coming up with a null hypothesis with the intention to disprove the null hypothesis so that your claim, the alternative hypothesis, is significant. Okay, if your dependent variable is IQ and then the mean IQ of the general population is 100, then the null hypothesis would be expressed as H sub O, H sub O colon mu equals 100. Okay, just remember on how we set up our null hypothesis earlier. And then step 2 is select the statistical test and the significance level. So otherwise stated in our problem, in our quiz, if it wasn't stated, then it's assumed that our alpha is 5% level, or it's on the 5% level of significance, considering that psychology follows the convention of 5% alpha in test hypothesis. And then, of course, we assign our statistical test, whether it's Z test, T test, F test, whatever test is going to be used. And then step 3, if you can recall, step 3 is select the sample and collect the data. Okay, remember last time, we selected 16 samples. In Dr. Tonin's case, we selected 16 samples, and then we collected the height of all the 16 samples, and then we computed our mean. I mean, that was the step 3. Step 4 is we find the rejection region. We decide whether it's two-tailed, considering it's two-tailed or one-tailed, and then we specify where is the rejection region. With anticipation that these three here can be used in interpreting the result. Okay? Or coming up with a decision. Step 5 is that's where the computation comes in, wherein you compute your sample mean. From our example earlier, there were 16 samples, and with 16, where there is the height of the 16 samples, we computed their mean, and then after that, we solve for the z-score. So all the computation happens in step 5. First is we compute the standard error. That is when the standard deviation of the population is presented or given. We compute the standard error, which is simply given to us as the quotient or the ratio between population standard deviation and the square root of our sample size. And then after which, when we have the standard error, we will solve already the z value, which is given to us as the sample mean minus the population mean divided by the standard error. And then the result of that, we have done already step 5. Step 6 is we now make a decision. We can make decision in terms of comparing the critical z and then the computed z. If the critical z is greater than the computed z, then reject the null. Otherwise, we can use also the p-value. If the p-value is greater than, if the p-value is greater than our split alpha, if it's two-tailed test, then that means to say if the p-value is less than the split alpha, if it's two-tailed test, then reject the null. If we wish to use the entire alpha, which is 5% for psychology, then we double our p-value. In this case, we double the 0.0038, giving us 0.0076, compared it to your alpha, which is 0.05. If the p-value is still less than the alpha, then still reject the null hypothesis. Okay? At least that's the summary of the 6 steps in performing a testing of hypothesis.
Sir, nalimot ko. Asa kinagikuha ang 0.0038, sir, kanang p-value, sir?
The p-value was taken when you have, this is your computed z, 2.67. 2.67, look for the probability distribution of this one in the z table. I'm not sure what's the value of this one. That value, subtract it to 0.05, the result is your p-value. You try to look for this one. What is the probability distribution of a z-score equivalent to 2.67?
Kato man ko na 0.
From the table.
0.4962, sir.
Okay. And then 0.5, 50%, half of the distribution minus that value. The result is this one. At least.
Thank you, sir.
Is it correct?
Yes, sir.
Okay. Any other clarification? Come on, you ask questions. Because that's the only way I can help you understand better the concepts if you are still confused. So if I may recall, the only part of the given here is we have the mean of the population, what was that? Which is 65 inches, and then we have the standard deviation of the population, which is 3%. Those were just assumed value. Their guesses were already computed. So it's like part of the given. As for, this is just a data that is, this is a pre-existing data. This wasn't based on actual gathered data. This time, I'm going to walk you through what are the constraints. When I say constraints, what are the things that you will take note in performing one sample z-test? First, okay. In performing one sample z-test, there are some assumptions underlying to one sample z-test. Okay? To do one sample z-test, we have to know the null hypothesis distribution. That is, we have to know that the group means are likely when you draw random samples of specified size from a known population. The null hypothesis distribution will be normal distribution with a parameters that are easy to find, but only if certain conditions apply. The following are the conditions that researchers must assume are met for the one sample z-test to be valid. Okay, like this. In conducting one sample z-test, you cannot just easily use sample z, one sample z-test right away. You have to consider some underlying factors that this task must be accepted, or at least must be observed in your data so that it is accepted. First is the sample group, mean the distribution of the sample group must be normal. Okay? Must be normal. First here, the dependent variable was measured on an interval or ratio level. Remember, there is independent and then dependent variable. In the conduct of using one sample z-test, the dependent variable must be measured using interval or ratio scale. You cannot use ordinal nor nominal. Remember, there is nominal wherein data was categorized, or data has categories, but the categories cannot be ranked. Like for example, the color of the eyes, the gender, or the sex of the respondent. These are nominal data. Nominal data that is measured in terms of nominal level of measurement, because you cannot compare, you cannot rank male or female, which is the first or second. Okay, and they are also non-quantifiable. You cannot count gender. Okay, like one is gender is one, male is one, two is female. You cannot count that one. Okay, and then yeah, the ratio level are the numbers that are continuous in nature. These are types of data that are continuous in nature, and then at the same time numerical, meaning to say this involves number, like temperature, height. These are example of uh, ratio level and ratio and interval level. So take note, ratio, when there is an appropriate, or there is a standard distance among scores or among entry. While interval, there's an interval level. So basically, once it's interval and ratio level, then t-test is z-test is applicable, or you can use it. Okay, that is when dependent variable was actually measured using interval. But if it's ordinal and nominal, you cannot use it. That's why there is always a dispute when your questionnaire is conducted or was measured in terms of Likert scale. I don't know if you're familiar. Likert scales are actually questions that is, example, you ask questions from your respondent like agree, disagree, strongly agree, neither agree, or nor disagree, then agree. These are ordinal level of measurement. The data was actually measured in terms of ordinal level. Although there is an ongoing dispute, that's why you can transform this information or this data, the Likert scale, into scale form by summarizing it. But later, I cannot deal so much with that one because this is just a segue of our discussion. But basically, in order for one sample z-test to work, your dependent variable, meaning to say the variable that is affected, highly affected with the independent variable is the dependent variable. So if this data is measured using interval or ratio scale, then you're safe to use one sample z-test. Okay? Next, the sample was drawn randomly. Okay? That's why earlier in the case of Dr. Tonin, the 16 samples were randomly selected. Okay? As you specify your sample size, okay, example, you identify that you need some 100 samples. Now, how you select the 100 samples from the population, it must be randomly done. Okay? Meaning to say, the meaning of random is that you give equal chances. Example, your population is 1,000. You only need 100. Now, to select the 100 from the 1,000, you give equal chances of all the 1,000 to be selected to be one of the 100. That is at least the idea of random selection. Because if you are biased, for example, you are just going to consider all those, example, 100 is your sample size from a population of 1,000. If you would only select your friends, you will select all your friends of the 100. That is not random selection. That is a what do you call this word? I forgot the term. Random, and then that is convenient sampling. You choose your sample based on your convenience, which is prone to bias. I mean, random selection still has a bias in it, but there is a small amount of bias found in it compared to uh, convenient sampling. Because convenient sampling happens wherein what you're going to do is, example, you will choose all your friends to be part of your sample because you said it's easier to consider them. So that's a violation already of random selection. Okay? So again, for one sample z-test to work, you need to consider a sample, or you need to consider um, a sample that is randomly selected. Next, the variable measured has a normal distribution in the population. So the variable measured, example, if it is your population should be normally distributed. Normally, the population would always tend to be normal, would tend to have a normal distribution. But the sample, okay, the variable measured has a normal distribution in the population. Strictly speaking, the sampling distribution of the mean will follow, right, will follow the normal distribution perfectly only if the population does. And we know that real world population do not perfectly follow a normal distribution, no matter what variable is measured. Fortunately, the central limit theorem says that even for the population distribution that are very far from normal, the sampling distribution of the mean can be assumed to be normal, provided that the sampling size is large enough. Okay, it's like this. The idea is like this. Your population should be normal. Okay? So that the distribution of the sample mean is also normal. But we cannot deny the fact that in a normal distribution of the population, you cannot expect that the distribution of the population is always normal. It is more likely that you will encounter a population that is not normally distributed. But according to central limit theorem, this is a theorem in statistics that says that even if the population's distribution is not normal, still it's possible to have a normally distributed normal distribution of the sample mean, provided that your sample size is large enough. Okay? So it says that the central limit theorem for any population that has mean mu and a finite variance of um, sigma squared, the distribution of sample means is based on n independent observations. Will approach to a normal distribution with mean mu and variance as n approaches infinity. So approaches to infinity here, it implies that as you move to infinity, as you move closer and closer to the population, even if the population do not resemble a normal distribution, it's still possible that the distribution of your sample means is still normal. It's because of the so-called, this is supported by the central limit theorem. Okay, that as you increase your sample size, it will more likely resemble it will resemble a normal distribution for the uh, distribution of the sample means. Even if the population mean, even if the population is not normally distributed. Okay, that is so according to the central limit theorem. Did you understand this theorem? At least you be bilingan because you're the one who read it. Did you understand the central limit theorem?
Libog, sir.
It's like this. Population and then samples. Okay? Take the population is considered, I mean, relatively large because we're talking about large group here. So, example, if you have 10 million from the population, okay, 10 million, and then you have a sample size of 100. So, you can come up with how many 100s out of 1 million with different representation. Just provided that if a member, if one respondent was already in one sample group, that member can no longer be a member of another sample group. Now, how many 100s are there in 1 million? Now, if you are going to get the distribution of the means of all the 100s you can come up, okay? So, the first 100, the second 100, second, third 100, these are your sample groups. If you get the average or the mean of this, whatever information you're talking about, of all the sample group, as you increase the sample group more and more and more, till you approach to infinity, the infinity here referring to the sample size or the population size, even though the population is not normally distributed, according to central limit theorem, the distribution of your sample means of all the hundreds that you've got there will still resemble to a normal distribution. That is what the central limit theorem is telling us. Okay? I hope I make sense with how I explained it to you. Did you understand?
Sir, so dili mag-coincide ang katungkuan, sir. Kay kung did I explain? Kung normal distribution ang katong makuha sa mga katong every 100 nga sample group, sir, ba, then ang katong mean kay dili, sir. So,
You didn't understand it. You didn't understand it. It's like this. How am I gonna illustrate it? Hopefully this will make sense. Example, this is your distribution. Your distribution is like this. Example, that's the distribution of the population. And then you have a sample group. In your sample group, if you're going to, example, you have different sample, you have 100 sample groups out of the population. These 100 sample groups, if you're going to also look at its histogram, okay, its presentation of data, it will resemble a normal distribution still, even if even if the population distribution is not normal. The distribution of the sample mean of the 100 samples you have would still resemble to a normal distribution as you approach to the population, the number of the population. That is what the central limit theorem is telling. So it's like saying now that even if the population is not normally distributed, it's still possible that your sample mean or the mean of the sample distribution is still it's still possible to be normally distributed so long as your sample size is sakto, and then as it moves further, I mean it's increasing towards the population's size. Did you get it? It's like this. At least, did you understand my point? I think it seems to be very, very abstract to you. I'll make another attempt of explaining it. It's like this.
Confusing kaya, sir.
Um, you have population. So example, in your population, you have, let's say, 10 million. That is your population size. So example, if it's women, we are talking about 1 million women. Okay? 1 million women. And then out of this 1 million women, you intend to have a sample group of 100. So the size of the sample group is 100. So you randomly selected. Okay, according to the previous assumption, you should have a sample group that is randomly selected. So you selected 100 samples. Okay, that's sample one. And then you get the mean of this sample group. Okay, the height of this, if it's height, the height of this 100 samples. And then you make another